which is I equal to, whatever, I equal to 1 to whatever, let us say lattice size is L, or it can be whatever length infinity. So what happens is that you have only one particle here at one position, which is called I, and what you do is that you just keep walking to the left or right. Okay, so each time what you do is that you toss a coin. If it is head, you go to the left. If it is tail, you go to the right. That's the random walk. Okay. So now question is that so what are the other thing you could have done? Okay. So point is that you could have done, let all the time you go only to the right. So if you start here, in next step you go here, next step you go here. If you go like that, in time t, you travel a distance x which goes as t, right? I mean, x equal to vt. That's the equation. So the distance you travel in time, in t time. Okay. So to travel a distance x, you need time which is proportional to x. Okay. If it is, and that's the kind of thing called ballistic. Okay. So to travel a distance x, so x goes as t. So the time which is same as x. Okay. It's clear, right? So if you are moving with a velocity, some constant velocity, then to travel a distance x, you need time which is proportional to x itself. Okay. So time is v by x. So this basically to travel distance x, you need time which is proportional to x. That much of time you need. Okay. So now if you are confused, let us say that you don't go to this, you do not know where to go. You don't go straight, you go left or right. Then what happens? So what happens to my? Oh, it's working. Okay. Okay. Sorry, I thought that. Okay. So if you are confused and if you try to go left and right, then what will happen is that to travel distance x, you need x square time. Okay. The time which is needed is x square, because the equation for this one is just a del rho or del p by del x, del p by del t equal to del square p divided by del x square. P is the probability that you are at x at time t. Okay, and that's the equation, the x square. So x square goes as t. That's the scaling. So x square goes as t. So time you need is x square. Okay, so that's the random walk, and that's the same thing in 2 dimension also, or 3 dimensions. So this equation that x square goes as t, that's the property of a random walk. Okay, so that's the property which is also, this is also diffusion. Okay, so x square goes as t is the property of the random walk. Okay, that's the general thing. So don't get confused, because you need more time to cross the same distance. Okay, and what I talked today is that by now you probably know what are the random walkers. So in 2 dimension, if you start at position this and you start going to left and right, go on a lattice, for example, like that. This is one walk. You start somewhere, let us say here, or somewhere in the origin here, and then you keep doing that. You create a path like that, left, right. And in 2 dimension, it is left, right, and up and down, right? I mean, you can go left, right, and up, down, equal probability. So that's the kind of walk you create, and so here many walks which are presented in different colors. So one walker is, that, let us say 20 walkers starting here, maybe more than that, 50, and each of them is a different color, and they start walking, and their paths are given here. So that's the equation which I wrote here, and when the velocity is 0, this is 0, you know that x square goes as t, and that's the property of the random walk. So I'm assuming this. I'm not going to talk about this. Okay. So this is just for your information. Okay, so I wanted to show you a video about this, how, so in a system, so let us look at this video. You can watch it here. So just look at this, this is just a particles in a box, and the particles are colliding. Okay, there is no other external, there is no other forces, and the particles are colliding, and you are tracked one particle. This is the yellow one. Okay, it just collides and it starts going like that. And if you watch for 1 minute, you see that the path which it creates is the random walk. Okay, so basically random walk is important because of this. If you have a collection of particles, okay, and if you take a tracer particle, some particle which you are interested, it will just keep colliding. So basically, the other particles, maybe they will behave like a bath, and this one is like a Brownian particle which is making some motion, and this motion is usually diffusive. Okay. So now people know in these kind of systems, because the particles just move diffusively, there is no direction. Which way it will go, you do not know. Okay. Eventually it will go in all directions. So in these kind of systems, yeah. It depends on what is the model. It's just a caricature I'm just doing. It's not doing details. So, so if you look at these kind of pictures, so now let us say you have some kind of potential which force the particle to go to the right more often than to the left. So, for example, in this kind of work, it was 1/4. This side is 1/4. This was 1/4. This was 1/4. And then what you say is that this is 1/4 plus q and 1/4 minus q. Let us say that you just bias particle to go to the left. So if you do that, then the particle will move that. So they will generate a current. Particle will go from from this to that. So that will be given by the biased random walk. So that will generate a current, but the intrinsic property of the walk will still remain random or diffusive. Okay. So what I am going to tell you today is that how this random walk or diffusion is related to transport in a system. That's my topic. Okay. Okay. So what I say is that, so what is transport? Now let us define what is transport. As I said that you have some system. Let us say this side is length L, okay? And then you have two baths. This side is some hot bath or cold bath, or it can be any other potential which you are giving, maybe higher potential, lower potential. So the potential is phi. So the general law is called J equal to del phi. Okay? If the phi is potential, then you call it Ohm's law. If it is phi is temperature, you call it Fourier's law. There are different laws, name it differently, but current is proportional to the gradient. Okay? So what is the meaning of that? You have a system and you put some bias. So there are two things you expect. Okay? One is that there will be a current, because particles are pushed like that, because there is a downhill. Particle will current, and current will flow in a direction of the gradient. Right? I mean, wherever it is low, current will flow that direction. Okay? That is one statement. Second statement is that if you increase the bias, some current is flowing, and you now increase the bias. What will happen? You have more current because you are pushing more. If you push more, you get more. Okay, there will be more current. So these two laws, I will be talking about these two violation of all these two statements. Okay, and I will try to convince you on that. Okay, so now, if you have a system and you have some potential, you have a current. Okay, and the current. So you can think of there are particles here which are either diffusive or maybe they are doing ballistic. Okay, so if they are diffusive, the time needed to travel a distance L is proportional to L square. I already talked it here. Okay, so now current is like a velocity, which is space divided how much space divided by how much time. So to travel a distance L, if you need L square time, your current will be proportional to 1 by L. Okay, so which is coming out from here also, like current in one dimension is a gradient, and gradient is d by dx, which is like 1 by L, delta phi divided by L. Okay, so a general law tells you that the current is always inversely proportional to the length of the system. So keeping the same potential, if you double the system size, current will be halved. Okay, same potential V1 and V2, but you double the system size, current in the system will be halved. That's a general law. But the property, the law comes from the fact that you are intrinsically assuming that the particles which are carrying the current are diffusive, because only when it is diffusive, then you travel a distance L, you need L square, and J is 1 by L. Okay, so that is this law and this law, it's consistent. Okay, so transport is related to the diffusion. You are intrinsically looking for diffusion. Instead, if it is ballistic, for example, to travel a distance x, like you just go like that. If you to travel a distance L, you need L square L time. Time is also L. Then the current will be independent of L. This is kind of a ballistic transport. Like in quantum walkers, we will give you a ballistic transport. Okay, and it will not follow laws like that. So in actually, if you look at quantum systems in a very low temperature, they don't follow this diffusive law, they follow a different law. There is the transport is actually ballistic. Okay, so what I'm going to talk today is that, there are particles here and they behave diffusively. But are these particles non-interacting? Of course they are not. So there will be particles which are primarily diffusive, but then there can be interaction between the particles. Okay? So basically what I'm talking about, current in an interacting particle system. So then this in an interacting particle system, you have many modes of transport. I'm using a new word called modes. So that is can be particles, or it can be different modes of transport, like it can be some other degrees of freedom, quasi-particles or something else. Okay, so for a general name, I will not call particles. I will call them rather modes. Okay. So now current in interacting particle system can be described like that. So you have many modes. Some of maybe some of them are diffusive, some of them are not. Maybe all of them are diffusive and some are driven. Driven basically some which can see the external field, so other particles which do not see the external field. For example, if you have a collection of charged particle and non-charged particle, neutral and charged particle in a collection. Some particles are charged. If you put an electric field, only charged particle will see it. Neutral particles will not see it. They are interacting with the charged particle via some other forces, but they don't see the bias. Okay? So those which do not see the external drive explicitly, I call it non-driven. In a system, you can have non-driven particles, you can have driven particles. Okay? So now, I will see that interplay between these two, driven and non-driven degrees of freedom, can give you very nice, beautiful features, okay? Which is usually not possible to see in equilibrium systems. Okay? And so what I am going to say is that today's topic is that can current decrease with increasing bias? Okay? And the general idea is that you have a system and some current is flowing like that, and you increase the bias, there will be more current. Okay. So is it possible that you are pushing more, but the system is not responding, it's responding the other way, your current goes down if you push more? Is it possible? Okay. Other thing is that can current change direction when bias is fixed? So you have a bias like that, and then current was flowing like this in this direction. You change some parameter in the problem, suddenly current flow uphill. Okay. Is it possible? Okay. Both these things are not possible in equilibrium. Okay. I will try to argue for that. It is possible in equilibrium system, and I will give you some examples where it is possible in non-equilibrium systems. Closer. Okay. No, it can be two species of particles, it could be species, right, it can be different, it can be, modes can be anything. It can be two different modes. For example, modes of transport, so it can be same number of particles. You have particles which are coupled by spring, okay? You know this model, it's mass spring model. There are a lot of masses which are attached by spring. So you can have, they will vibrate and there will be some vibrational modes. So those modes are the one which will transport. So the modes are, it can be some collective modes, it may not have a particle interpretation. It can be species, different species of particles, it can be anything. No. So this is a good question. You cannot have current in the equilibrium system. So what current people talk about and what people measure, because nobody knows how to calculate current in equilibrium system. So what is the current? Okay. So what people do is, there is an argument people use. So you say that, okay, let me answer this. So the point is, you see, when you ask for current, you are only interested about the conductivity. Conductivity is a property of a matter. That's the way that you argue. Conductivity is a property of matter. Okay, so then should it depend on the potential what you use? So you say no. You say that then use potential V and V plus delta V. You ask me, what is delta V? I say delta V is smaller than any small number you know. So by that I am saying that you can actually ignore delta V in certain calculation. Okay. So you do only the first order calculation in delta V and you use as if the system is in equilibrium. Okay. So you have a small potential and you use the equilibrium properties because you do not know what is the non-equilibrium state. Okay. You still calculate the equilibrium property of the current and that's the current you do. That's called Kubo formula. Okay. linear response or Kubo formula. That's the only thing you know. In actually, if I tell you put V1, put V2, calculate current, I don't think anybody can calculate even Ohm's law. Okay, there is no way to calculate this. You have to know what is the system, how to couple, and it's a big question. Actual calculation of current. Okay, so now let me say, so this one, if current actually, so basically if you increase bias, current should go up, but if it goes down at some point, you call it that. So if it is current and this is potential, then di by dv is resistance. This slope is the resistance, right? So this side is slope is positive, this side is slope is negative. So this is actually, if the current show a behavior like that, you have a negative resistance. Okay, so that is called a negative response. That's what is called a negative response. So I will talk of negative response and current reversal, uphill current. If you have a bias like that, current flows in that direction. These two things I will discuss. Okay, so now let us say that why exactly in equilibrium you have, if you increase potential, the current will increase. Where does it come from? Okay, so I will argue for you. This is not the proof. The point is that let us think of a magnetic system. Okay, in a paramagnetic system, right? I mean, it's in paramagnetic system, and it is going through a transition. Okay, so now you can have average. In the critical point, you can have fluctuations, right? I mean, so for example, if you have a paramagnetic system, if the magnetization is m, and m square average minus m average square, that is what is your fluctuation. Okay, and this fluctuation is also related to how m changes with a small field at h equal to 0. Okay, I mean that this relation. Del m by del h equal to this. This is easy to calculate, right? So basically, the fluctuation is always related to response, and this formula is generally true most cases. Okay, so the point is that magnetization itself is a fluctuating quantity whose average is 0, right? I mean, the average is 0, but its fluctuation need not be 0. In a paramagnetic state, the fluctuation need not be 0, and the fluctuation has a value. So if you want to calculate what will be the fluctuation when you, right? I mean, what will be the fluctuation? Then that is same as how magnetization changes by putting a field. No, I did not say clearly. Let me say. So let us say that m average at some point equal to 0. Okay, that's a paramagnetic state. You now put a field, small field h. So that will be m average is a function of h. What is that? Okay. So all I am saying is that when you say that m average equal to 0, it's only the mean of a distribution is 0. There is a variance, and the variance here in this case there is no field, but the variance is some m square average minus chi equal to m square average minus m average square. Okay, that's the variance. Mean is 0, but the variance is some value. So question is that what will be if you put a small field? How much the magnetization will change? That will be same as h times this chi. This fluctuation. Okay, how? Because m of h equal to m of 0, h equal to 0, this is m of 0 equal to 0 plus h del m by del h. Okay, m of 0 is 0, h and del m by del h is just that. Okay, so this one is always positive because this is m minus m average whole square. Okay, this is positive. So if you have some quantity which is 0 mean, and if which can increase this quantity. So for example, here you have a 0 mean is in equilibrium, J average equal to 0. Now you say that you put a little bit of bias. So then that is 0 plus epsilon. Here it is better. Okay. So J epsilon, and that is J0 plus epsilon del by del H. Okay. And this one is just a fluctuation. So del J by del epsilon, this is like di by dv equal to J square average minus J average square, and this one is a positive quantity because this is just J minus J average square average. So this is positive. Okay. So which means the response is always positive. Di by dv, this is the resistance, that is always positive. Other thing is that J equal to epsilon J square. You look at this, J0 is 0, and this is epsilon times J square average minus J average square. So that is also J square average 0. Okay. So J if you put a small epsilon, that is epsilon times the response, which is positive. So if this quantity is positive, so the direction of current is same as the direction of gradient. Okay. The sign of epsilon is same as the sign of current. So this general argument tells you that current will always take the direction of the gradient. Current will increase when you increase the potential or voltage. Okay. So negative response is the, so basically, do you see it in equilibrium? Of course, ohmic systems behave like that. In semiconductors, it behaves like that, but it is always increasing. Okay. That's what happens. It has to increase always. Okay. So now what I'm talking about is that, in this, I'm trying to give you an explanation, or, in non-equilibrium system, this can happen. Okay. Current can go down and resistance can become negative. Okay. And other thing is current reversal. Okay. Now let us say that I talked about equilibrium, and to just set the tone and just to define what I call current, what I call bias, let us do a very simple problem. Okay. So the problem is that this is a one-dimensional lattice, and there is only one particle, and the particle can go to right more often than to left. Okay. So basically A, and there is all zeros. A0 can go to 0A, which means the particle moves to right with rate P, and it can go to left with rate Q. Okay. So the current will be just P minus Q. Okay. So that is kind of, generally you can see this. So let us see this. This is a 1D periodic lattice, there is only one particle. So the current, how to define formally? Number of right moves in time t. So you wait for sufficiently long time t, find out how many right jumps it does, how many left jumps it does. Those are NR and NL. But that is NR minus NL, and then you take an average of that, average number of right jumps in time t. So NR minus NL divided by t, and t goes to infinity. So if you wait for large times, the difference between number of right jumps minus number of left jumps is the current, right, divided by time. So now what is a bias? Okay, in this problem, what exactly is the bias, right? This is the problem which I defined. Let us define what is the bias. So to define the bias, let us say that bias basically means that you have a one-dimensional system, you have a potential like that. Okay. So if you have a potential like that, then this potential is just it's a linear one, A minus epsilon x, right? That's the potential. So the energy, because this site is only one, the change of energy is just epsilon, right? The change of energy from this to this. What is happening? Okay. Okay. So basically, okay, maybe this side is better. Okay. So basically, if this is a linear potential, so then if you move from this to that, the energy is decreased, right? Total. If this is the energy, V is the potential energy. If your particle move from here to here, the potential is decreased by epsilon. If you go from here to here, the potential energy increased by epsilon. So if you want to do a Monte Carlo of a particle movement of like that, it will like A0 goes to 0A. So going forward with rate 1, going backward with rate e to the power minus epsilon, right? That's the Monte Carlo thing. So this is the thing, is same as this. If you put P equal to e to the power minus epsilon, this is the same thing as that. One of the thing you can put it 1. Okay. So the bias is just P by Q. This is P by Q is e to the power minus epsilon by 1 log of P by Q. So then you get epsilon. Okay. So the potential, right? What is the, at what slope you are putting the potential, that is given by log of P by Q. Are you agreeing with that? The definition of the bias, I will say that if the particles move right with the probability P, with rate P, with left with Q, then the bias the particle is experiencing is log P by Q. Is it okay with everybody? And that's the definition, because if you have a potential with epsilon, then this divided by that gives you bias, log of this divided by that. Okay, log of right move, that's a bias. So now the current in this system, because this is just a single particle just moving round and round, so it will be everywhere. Probability that it is at anywhere is the same, equal probability. So then the current is the number of right jumps is just the time the t times p, right? And similarly left jumps is t times q. So if you just calculate this will be just p minus q. Okay, so the current is just p minus q, and then you have to plot p minus q, put p equal to 1, q is e to the power minus epsilon, and p minus q is 1 minus e to the power epsilon versus epsilon. This is a function like that, it's increasing. True. Great. I mean, that's what we want to calculate in many more times. Okay, next ones. Okay. So now say that, this doesn't work, right? I mean, what is our task is that look at models where current can be negative. Like, not current can be negative, current can be negative. If you put a bias this way, current will be negative. Response of the current is negative. Slope is negative. Okay. So that's what this is not the one. So let us put little more. So let's say many Walker. So you said that now instead of one, you put many. So then now there are many particles, but there is hardcore interaction between them. They cannot cross each other. So in this case, the dynamics remains same. P equal to 1 q is e to the power minus epsilon. Okay. So then this is in this case again, because there is a density, but all configurations are now equally likely. There are only, right, I mean, all this one will tell you only there are some 7 particles in this lattice. Where they are all equally likely, right? In the stationary state, they will be all equally likely. Okay. So then it is still P by Q, and then dj by d epsilon is still greater than 0, because dj by d epsilon will just exactly that, and the slope is always positive. Okay. So now let us complicate little more. Many particles, many Walker and exclusion. Many Walker, no exclusion. There are many particles, but there is no exclusion. Okay. So one model is that you have a lattice, and each side now can occupy many particles. Okay. And then the particle can move to left and right with p times some function u4, and the right move depends on u times u is a function, and 4 is the number of particles. So if the site has 4 particles, it moves to the right with p u4, left q u4. If the number of particles is 1, then the particle will move p u1, left is q u1. So this model can be also solved. I am not going to say details. People who has attended the previous lecture on this one, this refresher course, they know that current here will be Z, and Z is an increasing function of potential. So this doesn't work. All I'm saying is that this doesn't work. That's the message. Okay. So if you take many Walker, no exclusion, it will not work. The current is still positive. The slope of the current is positive. Now let us say that instead of one species, let us take many species. Right? I mean, let us say 2 species, A and B. So if there are 2 species, then what I do is that let us say species 1, A particles are biased. A particles are this charged particle, they are biased. So they go to right with probability P or rate P, and go to left with rate Q. Okay. But B is unbiased. B are the neutral particles. So they just go left right with same rate. Okay. They go to left right same rate. And now what will happen when A, B are close by? Should they exchange? Should they not? If you don't allow them exchange, then nothing much will happen, because you are stuck. Like number of particles, they are stuck in between. In this, you can imagine, because the number of particles between any 2 B's will be stuck if you don't allow exchange, and that's a restricted phase space. So that's not a good one. So we allow them to exchange with some rate alpha. Okay, both ways. A B can become B A. So that is the model. Okay. So if you take this model, I am not going to tell you how I get it, and this model cannot be solved, whatever, but if you find numerically that current is always greater than 0. So this is numerical results. Okay. So now,
is there any electrical induction here? Plastic induces minus?
No. It is a simple model, very simple thing when taking about. We can talk them. We can introduce it. Okay, so now another model. So let us say additional field on B. Here B was unbiased. Okay, so now what you put is that put a bias on B. Let us say B 0 B is phi and psi, some different rates. Then the bias on B particle is just log phi by psi. That's the bias by definition. And for any field, whatever field, fixed field, if you change P log P by Q, which is epsilon, if you change epsilon, you still get current is, slope of the current is positive. I mean, so question is that I am just describing failures, it doesn't work. So I have talked many particles with exclusion, without exclusion, bias one particle, more particle, it is not working. Okay. So now question is that where it works. So we talk same model, we take the same model, 2 different kind of particles, same, this is exactly the way it was, this is also, exchange is also there. But this B0, we put little more interaction. When B particle moves to the right, okay, this one, so B particle moves to the left with rate W, but B particle moves to the right. That right movement depends on what is in left. Okay, so what is immediate left? Tau. Tau can be A or B. Okay, so basically that means that 0 from because this side is not tau independent, W tau independent. So 0B goes to B0 with rate W. 0B, this tau is immaterial here when you go backward, but when you go forward, then tau matters. Okay, and tau equal to W when in this situation, when you have isolated, it is 1, and on other set it is 1. So if it is 0, it is rate 1. If it is 1, sorry, this is 1. Okay, if it is 1, it is rate W. So the point is that there are two different kind of particles. A particle is charged particle which is biased. B particle is not. B particle is also biased, but the bias depends on the right movement depends on who is sitting in the neighbor. So this is the interaction. It is looking at what is in the neighbor. It's the interaction. Okay. So if you increase this interaction, then we find that the current actually goes current goes up as you increase epsilon, and suddenly it goes down. Okay. Exclusion I have taken. Yeah, that's the whole story. So we'll go there. So this is what happens. So in this case it works. So now question that in this model, how many parameters are there? One is alpha, this exchange rate. Log P by Q is epsilon. Alpha, epsilon anyway you change. That's not a parameter. Parameter of course, but that will change. Alpha is fixed, and there is this W. W is another parameter here. Okay. So alpha and W are fixed, but also the density is a number of particles in the system, number of A and number of B. They are not going anywhere. They are fixed. So the density is also conserved. Okay. So what I say is that number of A is 10%, number of B is 10% of the lattice. Okay. B particles occupy 10%, A particle occupy 10%, and you see the response, the current versus epsilon. You see that A particle current is this, B particle current is that, and the current, both the currents actually goes up and goes down. Okay. So that's what we are looking for. So the resistance in this epsilon, for large epsilon, is negative for both A and B particle. But same thing, you keep, instead of taking B particle 10%, take 50% of the lattice filled with B. Okay. So 50% B, 10% A. If you take a system like that, then the current actually still it is increasing, always increasing with epsilon. There is no negative response. Okay. So basically just by changing one parameter you can see that it is happening. So this is the example where it happens. So now I am not going to tell you where it happens, and I am telling you general, my idea is to give you a very general idea why and where it can happen. Okay, not in one model. So now to see why actually, question was, can you any physical interpretation? Then for intuition you have to look at other quantities. Okay, so what are the other quantities? So you say that for any particle, right, so the number of right moves minus the number of left moves, you call that as current. Okay, but then number of right moves plus the number of left moves, that is another quantity, right? So basically if you have two parameters in a system, so you have a system, you have some particle, and this particle is going some number of times which is going to right is nr, and number of times it goes to left is nl. These are two parameters, and for a given time t, both that numbers are stochastic variables, right? There are stochastic variables. So now from this, if you want to construct, you can construct two other quantities which are also stochastic variables, j, which is nr minus nl. Of course, but that's incomplete. You should be constructing something called s equal to nr plus nl. I don't know what I define it here. So yeah, this, oh sorry, my notation is little different. So this j is nr minus nl, and what I call s here, this is written n here. Okay, okay. So sum and this one, these are the two different quantities. So instead of looking at current, we also look at what happens to this quantity, the sum. The sum is called activity, total number of jumps made by A or made by B. Okay. So nr plus nl is the total number of jumps. This is the quantity we are now looking at. Okay. Here we say that in this situation and these situations, here there was a negative response, here there was no negative response, and we are looking at total number of right jumps plus total number of left jumps of A and that of B. Okay. So this is both cases, this is plotted, and if you look at that, you can see So now if you look at this, then you can see that the red curve always follows the red curve. So current of A follows the activity or whatever this sum, activity is called activity or traffic. Current of A follows the traffic or activity of B. Okay? So this red actually appears like that. So this red actually like that. There is no relation between the blues. The blue looks like that, blue looks like that here, but here the blue looks like that, and here the blue, right, the current looks like that. So the activity of current A, the one which is biased, okay. So the activity, so what is happening is that the current in the biased modes depends on activity of the unbiased modes. That's appearing to be the idea, okay. So let us try implementing this idea, okay. So here what I say is that, so these are J primes, means this is the slope of the A current and activity of B current, okay. So here both of them are positive, which means that activity is positive and this is, the activity is positive and current is also, slope of the current is also positive. Positive response, positive activity, okay. So and then this, the whole region is, this line separates this region, okay. So this is negative current, negative mobility and negative current. I think I am not doing good in time, okay. Anyway, so the idea, did you get the idea? So there are, I think we will go fast, and at least two species. So if you have a single species, it will not work, single mode it will not work, you need many modes, okay. So you have diffusive modes and non-diffusive modes. I am not saying that that is the only mechanism, okay. This is one possible mechanism, okay. So let us go to the mechanism directly. So what is the mechanism? So what we say is that particle current in a driven many particle system might show a non-monotonic behavior, which means negative response, if some modes which are not driven by the external bias slow down with increasing driving, okay. So in a many particle system there are many modes, some modes which see external field, some modes which do not see external field, okay. So when you increase the external field, two things can happen. When you increase the external field, the one which see the external field, they are pushed, okay. But then it is possible that the same field is seen differently by the non-driven modes, okay. Their activity, they are diffusing, but they might diffuse slow, okay. So what is happening here in these pictures is that when you increase bias, the activity of this is slowing down. Activity was increasing initially, activity of B, which is not biased by epsilon. If you look at your dynamics, there are no epsilon here, epsilon is just P by Q, there is no epsilon here, everything is fixed. So even then the activity of B particle actually slows down, and when the activity slows down, B particle, this red one slows down, and that's the same time current of A also slows down. Current is the one, because you are biasing, you are forcing A, you look for current A. So the current of A goes down when the activity of the other particle which is not seeing the external field is also slowing down. That's the correlation which is here, and I am building up the idea based on this correlation, okay. So what I say is that in interacting particle system there are many degrees of freedom. So there are some which are biased, some of them are driven by the red ones which are directly driven by the external force, but then the other one also slow down by the external force. They might be diffusing, but they slow down by the external force, and in this situation you can have a negative response, okay. So that's the point. So I think okay. So if this proposed mechanism is correct, what I am saying is correct, then all these models which I talked about where there is no negative response, I have talked of 2, 3, 4 models where there is no negative response. I pick up all of them, any of them, and now slow down the non-driven degree, and I should be able to see that the system actually generates the negative response, okay. So I did that, and this is the model which I started, like this one, when if you look at earlier, there is no tau dependence here, okay. This was the model earlier, and there was no negative response. Now what I say is that psi is the diffusion, but psi depends on epsilon. Epsilon is the bias here. So here is P by Q is epsilon, this is also epsilon, okay. So then also it slows down, okay. So if psi is a decreasing function of epsilon, then you can get negative response, okay. So that's the whole point. So earlier, if you look at the same model, I have discussed this model earlier here, no, not here, here, this same model. Okay, this model there was no negative response, but now what I make is the psi make a function of epsilon forcibly, because that was my task. I forcibly slow down B. This was diffusing mode. This was not seeing the bias. There is no epsilon here. Now I slow down this with epsilon. So I put epsilon here and I take a decreasing epsilon as a decreasing function of psi, and then I see that there is actually current goes down. Okay. Yeah, current goes down. Take the other model, it also shows that, and so all of them. So I am not going to tell you the details, but all the models which I studied earlier, which was not showing negative response, I take some non-driven degrees and slow them down. Okay, that automatically the current goes down. Okay, so that's what happened.
So you have to have some interaction between the modes, which is generated by this.
Yes.
Like you said that a particle jumps depending on what is there on the left or right.
Yes, so that was the first one. You don't, but now you don't. No. So in the original model, let us look at this. In the original model, wait a minute. In the original model, there was no dependence, okay, and that was not showing negative response. One way to say get negative response is to you make a psi. There is no interaction. There is no interaction. There is no additional interaction. I just make psi as a function of epsilon. I still see negative response. Interaction was anyway doing it, and interaction is a problem which I cannot handle very well. And I am saying that the effective dynamics, effective description of this interacting model, this effective description of this interacting model is just that. So whenever the traffic of B goes down, whenever B particle slows down, current of A actually goes down. That's the point. Okay. So that's the one which is happening, and I'm showing that this is actually true if you forcibly do in other models, right? So that's what I try to show. There are many models which I'm not, right? This is only one work, but I know we discuss several models just to sum up, just to say that this is the phenomenon. Okay. Okay. So before this, right? I just wanted to tell you a very simple model or a very simple system, or to give you a feeling how negative response can occur, right? In what situation you push particles more, but the current will not increase, current will rather decrease. Okay, so this is a very simple situation. I think you will understand it very well. So let us say that you have a box, you have a channel like that, and the channel has some kind of combs which is periodically placed. Okay, so this is the box, these are the boundaries, these are hard boxes, hard walls. Okay, so these are the walls, and there are particles which are flowing like this. And I wrote it okay. So this is I write it as rates, but instead I take this one. Okay. So particles forget about this. What is the dynamics of the particle? Dynamics of the particle is given by this. So particles go up and down with with probability 1/4, goes forward with probability 1/4 plus q, go backward with 1/4 minus q. Okay. So the bias is now log of this divided by that. Okay, that's your bias. So now what will happen in this situation? Okay, now particles are trying to move forward. So now if you put q equal to 0, then what will happen is that particles are diffusing, like going left and right. Some particle will go here, but so the forward and backward movement of the particle is the same because it is just 1/4. So then it will still have the chance that it will come back and escape this trap and goes forward. Okay. So for small q here, the current will increase as you increase things. Okay. So for example, for q equal to, if you take here 1/4 plus 0.001 or something, so there is a bias, but that will not be affected because each particle which is trapped in the wall, they try to move forward, but that is equal probability, almost equal probability, 1/4 plus epsilon q, 1/4 minus q, and q is very small. So with the same probability it is also coming back, so it will escape the trap. But if you increase too much, let us say this q is 1/4, then it will always, right, it is stuck here, and all the time it is trying to hit the wall, right? It cannot go up, it cannot go down, it is all the time to hit the wall. Okay, there is no chance of going back because backward rate is 0 or small. So then in this situation, what will happen is that most particle actually will be, just leave in the trap. Even if you push more, they will more and more leave in the trap. So they will not contribute to the current. So the current will go down in this situation. Okay. So if you increase bias, current will go down in this situation. Okay. So what is the mechanism here? So what is the mechanism here is that the number of particles which are taking part in current, those goes down. That's the way current goes down. You are forcing, that forcing is going up, but the number of particles which are, same particle, the number of particles which is, taking part in carrying current, those goes down much slower than the current can go up. Maybe it is 1 by epsilon square or something more than that. So your current, so the basic point is your current is that, right, you increase by putting a field epsilon, you are increasing like that, but then, so the total number, so this is the current, but the total number of particles which is carrying the current, which is also a function of epsilon in the interacting system. And this one goes down as, let us say, 1 by epsilon square. So the total current is this times that, which is 1 by epsilon. Okay? So that was the mechanism. That is the simple mechanism.
You are with a non-interacting, and
This is a non-interacting particle, completely non-interacting particle.
then you are talking about dynamic capitals. So there you talk about interparting.
Yes. So I'm just saying that I'm explaining one particular example of non-interacting particle where increasing bias can give rise to negative response. And there, here in this situation, the mechanism is that the same particle, the number of particles taking in carrying current, they goes down. This is one mechanism, okay, for non-interacting system. For the interacting system, I tell a different mechanism, okay. The mechanism is different one, because you have a, you are not slowing down the A particles which are biased, particles which are taking, that is not decreasing, okay. What is happening is that the slowdown of B, another particle, okay. You have many particles, those which see the, here you are directly slowing down the particles which are taking part in current, you are directly slowing them down. In the other one, it is, you are not doing that, you are slowing down something else, as an effect you see a negative response in some other set of particles. That's the difference. So here this one is a transparency to tell the difference. This was known earlier, 13, and the one which I talked about in 2018. Okay. So this is the difference. Okay. So I think I will not tell the details. It's not okay. So the main part. Okay. So what I wanted to tell you that the same situations I want to describe it. If you are still, if you are not hungry, at another 5 minutes I will tell you only 2 occurs. Okay. So let's say you have a ring. Okay. We describe this and we are done. So we have a ring and you have only 2 random walkers, simple random walkers. Okay. So this problem is also related to the problem discussed by Luca. So there you have these animals. You have a ring. You have these animals, 2 animals. One is red, one is blue, one is green. But then there are also walls. One wall is here. So the walls are effectively diffusing. So now you can think of these 2 things. So firstly, the walls are diffusing. So thereby making cages. And in the cage, there are animals which are only doing random walks. Okay, I am only discussing the cage problem. There are 2 walkers which are just doing like that, and I have exact solution for that. So that's what I am talking about. Okay. So we have 2 walkers A and B. A is biased, doing a biased random walk. B is just diffusing, simple diffusion. Okay. What will happen in this situation? And there is a hardcore. They cannot cross each other. Okay. So what will happen to this situation? Okay. So now intuitively what you can see is that because you have A particle, they cannot cross each other, although B particle is just doing left and right with equal probability. Just because A is pushing by forward, so it is trying to do left, but it's next time A is somewhere else. So effectively B particle will also generate a current because of this interaction. Simple interaction, hardcore interaction, A particle, just biasing of A particle will create current in B particle. Okay. So now this is statement 1. Statement 2 is that current of B particle is same as A particle. Why? Because they cannot cross. So the current is how many turns it will make in one direction. But it cannot make turns more than the number of turns made by the other particle because they cannot cross. So the current of A has to be same as current of B. Okay. So these are the 2 things. For the solution of this problem, right? So what you can say is that after a long time the situation will go to a stationary state, and I want to describe as a stationary state as a probability of a configuration is trace of as if, so okay, let me say, so in any configurations, what are the things? You have only A, B somewhere, and everywhere there are zeros. Okay. I will replace by some matrices. A is by matrix A, B is by matrix B, and 0 is by matrix E, okay, and that's called a matrix product state. So what I write is that probability of a configuration is just trace of corresponding matrices. So basically probability of 0, 0, 0, A, 0, 0 is trace of E, E. This A is a matrix, this is the way I write. And if you do it like that, and if you impose these dynamics, no, what is A, what is B, and what is E as a matrix? Of course I don't know. I'm just putting answers at this stage. I don't know. So what if you, you do not know. Nothing you know. You just introduce as a matrix. This is just answers at this stage. Okay. So I'm just saying I will try to calculate the dimension. It will come out as a, some algebra.
Dimension also you don't.
I don't know anything. No, we don't know. At this stage we do not know, because it just schematically writing any configuration which is unique can be written as A, and if you replace by is a matrix product, and just because you are writing a probability, you put a trace. So it's a matrix product taking a trace. It becomes a number, and the number is invariant if you rotate the configuration. But trace is also invariant. Rotate the configuration. So it's same.
No, trace is invariant. All these are finite dimensional matrices.
Yeah. So I'm just saying that so in that true.
So the first thing, the matrices have to be finite dimensional.
Not necessarily, right? It's no.
Otherwise you cannot in all invariance properties of matrices are true only for finite dimensions.
No, that's not true. No. Infinity, it is not that infinity matrices, all infinity matrices cannot satisfy the rule.
No,
It's
I'm
not,
saying
when a matrix
finite dimensional matrices.
do not satisfy, this is not a statement. You cannot guarantee that.
No, it doesn't matter.
No, trace AB equal to trace
Trace
BA
is
only
not
for
satisfied.
infinity.
It's not satisfied. Trace AB is not equal to trace BA if you have.
No. There are matrices.
Matrices are finite.
No. That is not a statement. There are matrices.
If you calculate XP.
No. For that matrix, that is not true. For that matrix, it is not true.
XP equal to IH cross.
It is not
taking
true.
trace of both
But I will
sides.
give you two other matrices for which it will.
Infinite
satisfy.
dimensional.
Yes.
Then you have to say that the diagonal they have only finite number of IH.
But if they commute, take two infinity matrices which commute with each other.
Huh?
Take two infinity matrices which commute with each other. You don't know any two infinity matrices which commute? I can write it 1, 1, 1, 2, 2, 2. They commute with each other. No, I mean, that's not true. The statement is that okay, we'll discuss this. I mean, but that's not true. That all infinity matrices will not satisfy this. There are infinity matrices which will satisfy this.
No, you see, you have to make the trace finite. That means you will be having zeros.
No, but infinity matrices cannot have finite trace is not a statement also.
Huh?
Infinity matrices can have a finite trace.
They can have finite trace.
Yes.
I'm not saying that. They cannot have. What I am saying is
Trace AB, the
Trace-
cyclic property holds only if the
doesn't
matrices are finite.
Cyclic property surely holds for finite dimensional matrices. Statement, I agree. The cyclic property will also hold for two specific infinite dimensional matrices. It's also true. I can find examples where it holds. It will not hold for all infinity matrices. I can find examples. So what is wrong with that? I can find example of infinity matrices where trace of AB is trace of ABA. I can find. I'm just give you example here. I give you one. Infinity matrix, just writing. I'm writing you one. What's wrong? 1, 1. Another matrix is 2, 2.
no, these are diagonal matrices.
No, but I mean, what is the diagonal? We are talking of infinity, na?
No, these are diagonal matrices. Diagonal matrices commute. That is not.
Okay.
These are not. These are trivial. So they will commute. I mean,
Yeah. I mean, maybe this is not example, but I can always find one. If you give me some example, don't ask me to.
point is, you can have infinite dimensional matrices commuting. That's not that. I am not saying that.
Huh.
I am saying it. The properties of matrices that we know of are true only for finite dimensions.
True.
You cannot extend it to infinite dimensions.
True, but it is not that okay, anyway.
So I think the statement is you may be able to construct specific
One. Examples where it is infinite
in
dimension.
general they are not.
No, in general they are not.
That's what I'm saying.
I'm also saying in general it is not.
So that means your result will be only true
No,
for those specific reasons.
no, but it is also true for infinite dimensional matrices which satisfy those.
Yes,
That's the same.
But
So you have to construct them.
I construct them. I do not know them at this stage, so I do not know the dimension. I can So at this stage I do not know what is the dimension of matrix. I might find a finite dimensional matrix which satisfy this condition. I might also find an infinite dimensional matrix which satisfy this condition. I don't have a problem. Specific ones satisfying given conditions. So now, okay. So now I start with this, and then this is the trace of probabilities written by a trace. Okay. And now what I do is that these matrices are at this stage not known, but you have to know something, because the dynamics will tell you what will be the condition on the matrices, algebra of the matrices, because you know any problem which have A, B and 0, as many A, as many B and as many zeros, okay, any dynamics can always be represented like that, right? I mean, if I am saying that this I am making an answers for any number of A, any number of B, any number of P, I can always write that, I mean whatever the dynamics. So this is very non-specific. That's the reason I do not know the dimension, I do not know anything, what are the matrices and what. So now, given this as a dynamics, I have to find out what is the condition this A, B and E satisfy. That's called a algebra, okay. How I get a algebra, this is little tedious, I will not tell you now. People who have,
So these are the deformed algebra.
these are Q deformed algebra, okay. So for this algebra, so like say P A E minus Q A equal to A, deformed Q algebra, okay. So now, so these are the conditions has to be satisfied by A and B, and given an algebra, you can have a representation, okay. So the representation can be, for example, I can tell you.
But it cannot, but it will not be unique.
You will not be unique, I don't need that.
So the representation of these type of
So for example, anything, let us say that for this I have taken a representation which is 2 by 2 dimensional, okay, but I can always construct an infinity dimensional matrix. Now, just now in front of you, for example, A is written like that. I consider a matrix A which is just A. This is not a diagonal matrix. This will still work.
Yeah, because the algebra
Algebra is the same. So algebra, a particular algebra satisfied by a finite dimensional matrix can always be satisfied by an infinite dimensional matrix.
with a specific restriction.
But I mean, no, this is but the algebra.
So that is not, that means you are not taking over the algebra of usual matrices.
No, I mean, because this is, you know, it's not a matrix. Algebra defines what are the matrices, right? If I say that A dagger equal to delta something, that defines the matrix, okay? So anyway, so this, okay, I think I'm not, we are going to unnecessary wrong directions. You know, so we can discuss those, but you know, this is nothing to do with the problem. And I don't know whether I have time. I think I, but anyway, so I think this problem works. You know, so do the rest, because I don't have time, and I think I stop here. Oh, if you want to continue me a little more, I can continue. Okay. Okay, so what you do is that, so now this is the algebra. So given an algebra, I can find matrices, and the matrices are 2 by 2 dimensional. So let us see, just do some quick calculations if you can follow this. Let us do this some very quick. So what happens is that you have a, and now if you want to write a partition function for this kind of systems, so all configuration starts like, you know, there is a and there is somewhere there is a b, and there is some number of e. So I say that e to the power k. So if it is e to the power k, then rest is e to the power l minus 2, because these two are gone, l minus 2, and k is also gone here, l minus 2 minus k. So this is a trace of that. That is probability of one configuration, and ek can be anything. So k equal to can be 0 also, because so this is trace, and k equal to 0 to infinity. And A by representation, A is a matrix just 2 1. Okay. So this trace can be written as, so this is just trace of 2. So 2 1, A is 2 1, B is 1 2. Okay, 1 2. So if you do that, so this will be 1 e to the power k 1, and 2 e to the power l minus 2 minus k 2, okay, and summation over k. And e to the power e is a diagonal matrix. So if you put e to the power k, that means this will be r to the power k. So this is, and e to the power l minus 2 minus k 2 2 equal to just w to the power that, okay. So this partition function is just summation over k, w to the power k, and here this is e, first one is r, so this is r to the power k, w to the power l minus 2 minus k, summation over k equal to 0 to infinity, okay. So that's the one. So this is just very simple sum. You can say that this is w to the power, no, not 0 to infinity, k equal to 0 to l minus 2, because this k can at most be l minus 2, okay. So basically this is the one. So this is w by, So if I call W by, so that's the matrix. So if I call W by R by W equal to alpha, then this is just a geometric series sum L minus 1 by 1, and W to the power L minus 2 remains here. Okay, so that's the one. So now if you want to calculate this, a partition function. Now, so now let us look at the current. So for the current, you know that A goes forward with rate P and A goes backward with rate Q. Okay, so this difference is the one which is current. So current is just P times AE minus Q times EA average, but P times AE minus Q times EA equal to A. So this is just, this one is just A average, but now you have AE, you are replacing by 1A. Okay, so the size is now reduced. So this is A average in a smaller system, smaller size system. So this A average L minus 1. So this, if you look at this is just partition function L minus 1 divided by ZL, and partition function is just right, this factor will cancel out. This is just 1 by W, because this L minus 1 by L is 1 by W, and the partition function, this is the current, and if you look at the current, this is just psi times P minus Q divided by Q plus psi. That's the answer. Okay, simple way I calculated it. So we go there. What is the problem? A is biased, doing a biased random walk. B is doing a simple random walk. Okay, just left and right. So the current in this situation will be just psi times P minus Q divided by Q plus psi. That's the current. Okay, so now we put, like if you want to make correspondence with bias, you put P equal to 1, Q equal to e to the power minus epsilon. It's a simple calculation. That's the one I'm putting it here. You put it here. Okay, if you put it here, then you get whatever value as epsilon, and you differentiate now current with respect to epsilon, you get psi divided by 1 plus psi. Okay, so this one, if you take epsilon goes to infinity, this is just psi prime divided by 1 plus psi whole square. Okay, and this 1 plus psi whole square is a positive quantity. Psi prime is the one on which this one will depend. Okay, the derivative of current A depends on psi prime. So psi, initially I was considering this in the model, psi is independent of epsilon, but if I put psi as a function of epsilon, and I see directly, I see here that when psi prime is negative, current is negative. Okay, so as a conclusion, so there are two particles. So these are kind of modes of transport. Okay, one is biased, one is not biased. So psi prime equal to 0 means that the field which was forcing a particle to move forward also slowing down diffusion of B particle. Okay, then you can have a negative response, any decreasing function. Okay, that's what I proved. Okay, and the problem, for the first year student, I'm just saying that the problem is very simple, right? 2 by 2 matrix, how hard it can be, and just 2 particles on a lattice. So you should be do it if you have the. Okay, so I just here, and I wanted to tell about some experiments, but I think I will stop here. Yeah. Okay. Yeah, in the during lunch, yeah, because it's all.
Please come back by 2:30. So the next talk will be by Skype. So it's very important that we are on time.
2:30. Yeah, okay.